Hi, in this video, I want to look at protein phosphorylation dephosphorylation cycle. This is what I've got here. I've got a unphosphorylated protein S, which gets phosphorylated to P via a kinase on the upper arm and a phosphatase in the lower arm. Let's say that the reaction rate for the upper arm is V1, the reaction rate for the lower arm is V2, and let's say I'm going to perturb the system by perturbing E1, which is the concentration of kinase. What I'm interested in doing here is using MCA, metabolic control analysis, to show what conditions are required for the system to show ultrasensitivity. Okay, so what I'm specifically wanting to look at is this coefficient. So if this coefficient is greater than 1, then we have ultrasensitivity. Okay, if it's less than 1, then it's not. All right. So how can we go about this? Well, there are various ways you can do it. I'm going to show you one particular way, uses implicit differentiation. It's fairly straightforward once you get the hang of it. So let's start. So what I'm going to do, first of all, I'm going to write down the rate of change of dp by dt. That's just V2, sorry, not V2, V1 minus V2, okay? And at steady state, that equals 0. So we're going to look at, obviously for the MCA I'm looking at the steady state. So I'm going to look at what happens to the steady state value of P when I perturb E1. Okay, now E1 is coming in to perturb V1. E1 could be a signal, it doesn't have to be E1, but this is a good place to start. So the first thing we need to do is expand V1 and V2. And that's pretty straightforward to do. So let's write that down. So dp by dt equals V1. So what I have to write down here is what V1 is a function of. Well, I know that V1 is a function of E1. So I write down E1. I also know it's a function of S. Oh, by the way, I'm going to assume that these reactions are irreversible. Okay, so V1 is only a function of S. So it's a function of S. Okay, function of S. But S is not an independent variable, it's a dependent variable, and S itself is a function of E1. Okay, so if I change E1, I will affect S. Okay, all right. So that does V1. For V2, V2 is a function of P. Okay, so I can write down P. But P is also an independent, is a dependent variable, and it's dependent on E1 as well. Okay, so P is a function of E1 as well. All right, so this is my full functional equation. It equals 0. So what I need to do now is I need to be able to, what I'm after is, if you think about this thing here, what I'm after is dp E1 P1, or dp E1 times E over P. So the first thing I'm going to try and do is get hold of this, and I can get hold of that by implicit differentiation of this equation here. So let's do that. So first of all, we'll start. So the right-hand side was 0, so I just get 0 there. But the left-hand side I can differentiate. So dv1 by de1 plus dv1 by ds, and then by the chain rule, ds by de1 minus dv2 by by dp, and then again by the chain rule, dp by d1 equals 0. Okay, now you can see this is the term I'm after, but I've got one little problem here. I've got this expression here, which I don't know what that is. So how are we going to get hold of this value here? There's an additional piece of information that we can use. If we look at the cycle, the total mass of the cycle is fixed. So S plus P is actually fixed because we're not there's no production of S from anywhere else, and there's no production of P from anywhere else, and there's no degradation either. So the amount of mass in this cycle is fixed. So I can safely say that the sum is sum total, okay? If I just rearrange that, so I get T minus P, I can differentiate that with respect to E1, and I will get ds by dE1 equals, T is a constant, so that stays at 0, minus dP by dE1. So what I can do is I can take this term and substitute it into there. All right. So let's do that. So let's see. So it's dV1 by dE1 plus dV1 by ds. And now there's a minus sign, which you mustn't forget. dP by dE1. Then it's minus dV2 by dP. And then it's dP by dE1 equals 0. Okay, so now I've got all the terms I need. This is the unknown. This is the thing I'm trying to find. Okay, so I can collect those terms together. The other thing I have are these other things. These things will turn into the elasticities, which is what I want as well. So if I rearrange this, let's see. So dV1 E1 plus, actually let's do minus dP dE1 times dV1 ds plus dV2 dP, that equals 0. So I end up with that. I can move this across the other side, so I get positive on both sides, and then I can compute, I can rearrange it to get dP1 E1, which is dV1 over dE1 divided by this thing, the denominator, plus dV2 dP. Now, what I'm after, of course, is dP. I'm after the scale version, which is this. Okay, I'm after the scale version. So to get that, I'm going to have to scale these terms. That's actually quite straightforward. So what I'll do is I'll multiply both sides by E1. Okay. I'll divide both sides by P. Okay. Divide both sides by P. Now, the other thing I also know is that at steady state, V1 equals V2. Okay, so I can divide both sides by V1, but I can put a V2 here because it doesn't make any difference because it's the same as V1. And then finally, this here, I can multiply top and bottom by S. Okay, so that then leads me with this thing here turns into the scaled control coefficient. This thing here is the enzyme elasticity, and we'll assume that to be 1. In other words, the reaction velocity is proportional to the amount of kinase, which is reasonable, divided by P over S. This is the elasticity of S on V1, and this is the elasticity of P on V2. The other thing I'll do is I'll multiply top and bottom by S, so S over P E1S plus S E2P. These are, of course, concentrations. I can get rid of concentrations by dividing top and bottom by T. And that means that these things turn into mole fractions. So I end up with CP, which is the final result, is the mole fraction of S. Remember, the mole fraction varies from 0 to 1, times the mole fraction of P, epsilon 1S, plus the mole fraction of S times E2P. And this is the final result. What can we say about this then? Well, remember, this is for this cycle, okay? The ES1 is that elasticity, and EP2 is that elasticity. So let's assume that both reactions are unsaturated. They're working in the linear range. That means that both of these will equal 1. And so in the linear range, when the enzymes are kinase and phosphatase are unsaturated, we end up with with that. Now, of course, this thing here, the sum of the both mole fractions equals to 1, so I end up with ms. And since I know that ms varies between 0 and 1, I know that under these conditions, CPE1 will be less than or equal to 1 or greater than or equal to 0, okay? When E1S equals 1 and E2P equals 1. And remember, I said way back here, I said we get ultrasensitivity when that control coefficient is greater than 1. It's clearly not greater than 1. In fact, it's bounded between 0 and 1. So under these conditions, we won't see any ultrasensitivity. What happens, though, if the kinase and phosphatase are, more saturated? But let's think of an example, and we'll see what it looks like. Let's say that the elasticities are 0.2. Oops, that's P. Sorry. 0.2. Okay, so they're that means that the enzymes are both running above their KMs. Let's also set some values for the mole fractions. Let's say the mole fraction for S is 9, the mole fraction for P is 1. Okay. If I got that the right one? No, I don't want that. I would like it the other way around. Sorry. Let's make it like this. Okay. Actually, no. I'm forgetting now. Just make that like that. Okay. So those are the mole fractions of these are mole fractions, so it has to be 0.9 and 0.1. Sorry about that. Okay. These are mole fractions. They vary between 0 and 1. Okay. So let's substitute these values then into this equation. So we get CPE1 equals, so the mole fraction is 0.9. So that's the MS. MP is 0.1. Actually, it's easy to put the elasticity in first because both elasticities are 0.2. I can pull out the elasticity 0.2 times, and of course, I've just got the sum of MS plus MP, which is 1. Okay, so I get 0.9 divided by 0.2. And that, if I'm not mistaken, is 4.5. So you can see now that the sensitivity of the phosphorylated form with respect to E1 is much greater than 1. In fact, you can see that if the elasticities get lower and lower, this thing can get as high as you like, in fact. It's a much better way of getting very high sensitivities than, say, using allosteric control. Okay, so that completes that. So in summary, we started off with this system. Okay, we started off with this. We noted that the sensitivity of P with respect to E1 will give us an idea of how sensitive P is to E1. If that sensitivity is greater than 1, if it's greater than 1, basically the system is showing ultrasensitivity, otherwise it's not. We can write down the mass balance equation, V1 minus V2. We can expand that into the full functional forms, and then by doing implicit differentiation, we get this. We note that the sum of the masses in the cycle is fixed, and we can use that to eliminate this term here, and so we end up with an equation that just has that term. We can rearrange the equations, so I get dPE1 on one side. I can scale all the terms top and bottom by multiplying top and bottom by the various factors, and I end up with this. Okay, so this is the main equation. Okay, and now I can look at various conditions. For example, what happens when the elasticities are 1? In other words, the kinase and phosphatase are not saturated at all. We end up with this simplification. It turns out then in that case that the control coefficient is bounded between 0 and 1. If, on the other hand, the elasticities are less than 1, for example, 0.2, I can get very high sensitivities, which is in the region of the ultrasensitivity. Okay, thanks very much.